Okay, so we're culminating with chapter 7, where we're going to look at a system that has to be treated entirely with quantum mechanics. You can't use any kind of classical thinking whatsoever. Okay? And so your author calls this chapter Quantum Statistics. It boils down to whether or not a particle is what's called a fermion or what's called a boson. Because those different classes of particles behave very differently. Fermions, for example, obey the Pauli exclusion principle, which you've heard about. Bosons do not obey the Pauli exclusion principle. And that difference, there are other differences between fermions and bosons, but that's a key one. Okay? And that difference accounts for very different kinds of behavior. But that's where we're headed. So we've got to build our way up first to that. So the first idea in this chapter is we're going to introduce what's called the Gibbs factor. We had the Boltzmann factor in the canonical formalism of statistical mechanics. We're going to have the Gibbs factor, and we're going to introduce what's called the, you gotta love this name, grand canonical formalism. If you thought the canonical formalism was something, watch out for this. Okay?
Who comes up with these names?
Yeah, I don't know. That's a good question. Who came up with the name grand canonical form? I tell you who came up with canonical. Gibbs did. Gibbs came up with the name of canonical formalism. Again, canonical in the sense of the standard one, the go-to one, the one everybody uses most of the time. Although this one is actually used a lot too. Okay? So what's different between the canonical formalism and the grand canonical formalism? Let's talk about the physical conditions that apply in the grand canonical formalism. There's only one change with the canonical formalism. Remember, the canonical formalism, the physical conditions are the system is in thermal contact with a reservoir of temperature T, and the system can exchange energy with that reservoir. That's the physical condition for the canonical formalism. What are the physical conditions for the grand canonical formalism? You allow the system to exchange energy and particles with a reservoir. One change. In addition to allowing the system to exchange energy with the reservoir, it can also exchange particles. Okay? So here's our standard picture in the grand canonical formalism. There's the part where the system is, and here's the part where the reservoir is, and this combined situation is completely isolated from the rest of the universe, like that. So over here we have the reservoir. It has two key properties. It's got some fixed temperature T, and we're also going to need to know the chemical potential mu of its particles. Which, remember, the chemical potential tells you about the tendency for the particles to diffuse. If you have a region, you wouldn't necessarily in this reservoir, but if you have a region where the chemical potential is higher than in another region, then there'll be a tendency for the particles to diffuse from the higher mu region to the lower mu region. All right, now over here is the system. the system has a partition between it and the reservoir. And that system allows energy and particles to go back and forth. So energy can go either way, and particles, because there's are pores in that partition that let particles go back and forth. So I drew the little red arrows to represent energy going back and forth, and the green arrows to represent particles going back and forth between the system and the reservoir. The system, well, we want to talk about the energy given a particular state S that it's in, and we want to know the number of particles the system has, capital N, for a given state S. Two things for the system we're going to keep track of. The energy for a given state S and the number of particles for a given state S. Now we're going to do an analysis just like we did for the canonical formalism, but will allow both energy and particles to be exchanged. So what we did in the canonical formalism, we said, is this. We said, what's the relative probability of finding the system in two different states? Let's take this ratio. The probability of finding the system in a state S2 relative to the probability of finding the system in a state S1. Okay? So each of these is a probability of finding the system in state S, where S could mean either S1 or S2. System. And then we argued that that relative probability of being in state 2 compared to state 1 is really just determined by how many states the reservoir has corresponding to each one of these states for the system. Okay? And that is the multiplicity of the reservoir. So then we said that this is just the multiplicity of the reservoir for the system being in state S2 divided by the multiplicity of the reservoir when the system is in state S1. And remember, the argument goes that the reason this is what's important is that a particular state, say S1 of the system, is more likely if there are more states that the reservoir has that correspond to that, because that means the reservoir is easily able to accommodate that state, S1, for the system. Because it has lots of states of its own that are compatible with the S1 for the system. So that's why the multiplicity of the reservoir is important. So this is the multiplicity of the reservoir when the system is in microstate S. That's either one of these. Okay? It's just how we did the canonical analysis. Exactly how we did it. Okay? And then the next thing we did in the canonical analysis, I'm going to do the same thing here in this new analysis. I'm going to remember that the entropy of the reservoir, by our definition, is Boltzmann's constant times the natural logarithm of the multiplicity of the reservoir. That's our definition of entropy. This case being the entropy of the reservoir. So I will just rearrange that by solving for the multiplicity, omega sub r. That'll be e to the s sub r over kb, and replace these with e. E to the entropy of the reservoir when the system is in state S2 divided by kb in the numerator, and e to the entropy of the reservoir when the system is in state 1 divided by kb. This very much a step in a right direction to go from here to here, because exponentials have such wonderful mathematical properties, such as I can bring this upstairs and change the sign on this argument, and then combine it with the argument up here. So now I have E bracket, entropy of reservoir for system state 2 minus entropy of reservoir for system state 1, close bracket, all divided by KB. That's great, 1. Then, just like I did in the canonical approach, the next step is to apply the thermodynamic identity for the reservoir. I will do it in terms of differentials, because I'm going to think of that as a difference between two entropy values, but I'm going to think of that difference as being small, because the reservoir is big. And to change the system state from S1 to S2 is probably not going to amount to a big change in the entropy of the reservoir. So I'm going to write it in terms of differentials. That difference, think of that as a delta SR. I'm going to write it as a DSR. And this comes from the thermodynamic identity. That's equal to 1 over T times du for the reservoir plus PdV for the reservoir minus mu dn for the reservoir. All right? Thermodynamic identity for the reservoir. This DSR is a representation of this difference up here in the argument of the exponential. Now we're going to specialize this because we have specified physical conditions. That partition there between the system and the reservoir is assumed to be immobile. Cannot move. So there can't be any change in the volume of the reservoir. Next, just like we did for the canonical approach, I will change this term, a tiny change in energy of the reservoir, to this, the negative of a change in energy of the system. You understand why you can do that? Because the total energy between the two parts is fixed. So any energy change in the reservoir has to come at the expense of the energy of the system. Right? So that is the change in the energy of the system. Change in energy of system. Now, one more thing, and this is different than the canonical approach. In the canonical approach, this partition was not porous. No particles could go back and forth. None. So the DNR is 0 in the canonical approach. But now it's not 0, because particles can go back and forth. But the total number of particles between the two things together, fixed. So any change in the particle number of the reservoir is just going to be the negative in the change in the particle number of the system. Okay? So I'm going to change the DNR to a negative DN, where that means change in particle number of system. And it's very important, this step, because I'm changing, watch the words, I'm replacing changes in properties of the reservoir with changes in corresponding properties of the system. Because that's ultimately what I want. I want an expression in the exponential that contains properties of the system. Just like we had with the canonical approach. Alright, so let's write out DSR. Let's see what it looks like now. I'm going to factor a negative out with the 1 over temperature. Okay, it's conventional, a negative sign. Then in parentheses I'll have dE minus mu dN, where these are changes in the system, dE and dN. Okay? And now I'm going to use this in equation 1. So, probability of system being in state S2 divided by probability of system being in state S1 is e to the, well, there's going to be a negative 1 over t that goes with this 1 over kb, so there'll be a negative 1 over kbt, open square bracket. All right, for the dE, right, change in energy of the system. Well, the system, think of the system as transitioning between these states, 1 and 2. So the change in energy of the system is E in state S2 minus E in state S1. That's the dE. Then I have minus mu times dN. Think of that as N in state S2 minus N in state S1. That's the dN. Then just undo the joining of the exponentials. Have an exponential in the numerator that depends on state S2, and an exponential in the denominator that depends on state S1. And you'll have this in the numerator. E to the negative. Energy, state S2, minus chemical potential times particle number, state S2, all divided by kBt. That's the exponential in the numerator. And in the denominator, you'll have the same thing, except it will be for state S1. Energy for state S1, minus chemical potential times particle number for state S1, all divided by kBt. And if you want, you can write the 1 over kBt as a beta. But the point is, this ratio of exponentials that gives me the relative probability of finding the system in state S2 compared to finding it in state S1 helps me identify what we're going to call the Gibbs factor for our system that can exchange energy and particles with the reservoir. The Gibbs factor is E to the negative energy for state S minus chemical potential times particle number for state S, all divided by kBt. If you want, you can write it like this. E to the negative beta times energy of state S minus chemical potential times particle number for state S. This is a biggie. This is just as important as the Boltzmann factor in the canonical formalism. Okay? This is what we'll call the Gibbs factor in the grand canonical formalism. Okay? Keep track, please, of things that depend upon the state label S of the system and things that are independent of the state label S. The energy is the energy of a specified state, so that does depend on S. The particle number depends upon the state, that depends on S. But chemical potential and temperature, those are fixed by the reservoir. Those are fixed by the reservoir. So don't put an S with the mu or the T. Okay? Okay, that's the new exponential factor in this new formalism. Now we have to figure out what's the appropriate partition function in this formalism. Okay? So we're going to have a new partition function. Remember, the partition function is really just a normalization factor. That's all it really is. It's not any deeper than that. It just turns out to be exceedingly useful. But it's really just a normalization factor. So now what I can say is that the absolute not relative, probability that system is in state, micro state S, okay, which I'll label P of S, will be, well, do you remember what it was in the canonical approach? It was the Boltzmann factor divided by the partition function, right? So now it's going to be the Gibbs factor, e to the minus energy of state S minus chemical potential times particle number of state S, all divided by kBt, Gibbs factor for state S, divided by what we will call the grand partition function, which I will denote as a script Z. That's my script Z. You may write your script Z other way. You might see it like this in books. Okay? What I recommend you don't do is write it like that. It's not exactly the same as the partition function in the canonical approach. Okay? So that's a script Z. That's my script Z. Okay? Where this new partition function, script Z, is determined by requiring that the sum over all the microstates S of the probability of each microstate must equal, wait for it, 1. Right? Let me show you, just like we did in the canonical approach. Okay? So, if that's what I require, and I do, that the sum over all available microstates of the system of the probability for each microstate must equal 1, because the system must be in one of the microstates, then let's see where that leads us. Sum over states of the probability of each state. Well, that's the Gibbs factor, e to the minus energy of state S minus chemical potential times particle number for state S, all divided by kBt, all divided by this new partition function, script Z. That sum must equal 1. Well, that normalization factor, script Z, is a function of two things: temperature and chemical potential, properties of the reservoir. It is not dependent on the index S in this sum. In other words, it can be pulled out front of the sum, and you get 1 over script Z, sum over states, of the Gibbs factor of state S must equal 1. Then multiply both sides by script Z, and you get script Z equals sum over the states of the Gibbs factor for each state. Well, this gets another box. Okay? That's how we will find the new partition function. And it is called the grand partition function. Equation 3. Okay. one thing I will mention is FYI. Sometimes a system can consist of more than one species of particle. There could be species A and species B and C and so forth, more than one species of particle. Then the way you generalize this, if there's more than one species of particle, and if these species are exchanged between the system and the reservoir, you treat each species as having its own chemical potential. Kind of like they're each existing on their own, independent of the others. And so, let's say your system had two species of particle, A and B. Then what you would have here is two terms. You'd have a minus mu sub A, n sub A for state S, and then minus mu sub B, n sub B for state S. Right? You have more than one species, so the bookkeeping is more complicated. But it's just more terms of u times n. Okay? All right, so, yes?
Is that like added?
Mm-hmm.
Okay.
That's right. So it's just another term added on. Of course, there'd be a minus sign there, but yeah,
Okay.
exactly. Okay? Exactly right. So what we've got to do is start applying this. Now, I'm not going to be able to do it. I don't think I want to start an example now. But here's, let me set up what you should expect. We're now going to start applying this to situations where it's convenient to be thinking about particle number changing, as well as energy. So your book has an example, which I'm going to let you read, and then I'm going to do one of his homework problems as an example. The example problem that he does that I'm going to let you read is the example problem of oxygen molecules binding to iron ions on a hemoglobin molecule. This is how we oxidize our blood. Right? Our blood contains hemoglobin, which has iron. The iron ions have locations on the ions where oxygen atoms can bond. And so when the blood is sent to your lungs, well, it goes up towards the wall of the lungs, it can come in contact with O2 molecules from your breathing. And then O2 molecules can bond to the iron ions in the hemoglobin in your blood. That oxidizes or oxygenates, I guess is the word, your blood. And then the oxygen-rich blood is sent through the body to nourish the cells. Yes? This is what happens biology. This is what keeps you alive. And he gives you some numbers for the energy of an empty iron ion. That's the slot where an oxygen molecule would go, but it's empty. Versus if you put an O2 molecule on there and bond it. Notice you're changing the particle number here. No molecule, n equals 0. One molecule, n equals 1. Okay? With different energies for the two states. No molecule's condition has a different energy than one molecule's bonded. Okay? All right. Then he looks, and so he can talk about the probability using the Gibbs factor of occupied with O2 versus unoccupied at a given temperature, human body temperature. Then he says, what if there's carbon monoxide in the air that you're breathing? Which everybody knows is deadly, right? If there's too much of it. Well, carbon monoxide can sneak in here and bond to, or instead of, O2. And that has a different energy associated with it. But that turns out, if there's CO in the air, it's a little bit more likely that CO will bond than OO. And then it's OO. Okay? Because your body can't use CO and take that to your cells. It won't help. You need OO. But CO is slightly more likely to bond than OO. So if there's too much CO in the air, that's what's going to predominantly bond to the hemoglobin, and you're in trouble. Okay? So he goes through some numbers with the Gibbs factor to show you that the CO is a little more likely than the OO, which means you don't want CO in the air, not at any kind of lethal level, because that's what your body will absorb, and it doesn't do you any good. Okay? That's an application of this approach, and this is where the changing particle number occurs. No bond, no molecule bonded, n equals 0. One molecule bonded, n equals 1. And different energies for each configuration. Okay? That's one application. Then the one I'm going to do, which is considerably harder, is the problem of dump a bunch of hydrogen atoms in a box. Fix the volume, don't let the volume change. And we'll vary the temperature. Okay? And we'd like to know, as a function of temperature, what fraction of the atoms become ionized? Just hydrogen atoms. So it means one proton bound to one electron, right? So to ionize a hydrogen atom means to just separate the proton and the electron. So what fraction of the hydrogen atoms become ionized? Free protons and free electrons as a function of temperature. That's important to know if you want to study stars. Okay? And that result is called the Saha equation. Have you heard that? Mm-hmm. Okay? That's a way to calculate the fraction of a sample of hydrogen that will be ionized as a function of temperature. And you use it, you get it from the Gibbs, or the Gibbs factor, or if you like, the grand canonical approach formula. Okay? So that's what I will show you. So you can read his example in the book about carbon monoxide bonding to hemoglobin, and then I'll do the one of ionizing hydrogen. That's what we'll do on Tuesday.
Last thing, but you can't conceptualize. Like 3 spheres and 4 spheres. Yeah, how do you have a line?